Effect of sulfate attack on rice husk. Ash-filtered sand self-compacting concrete. Abstract experiments were conducted to study the effect of rice husk ash and filtered sand on the durability property sulfate attack. In this study M70 grade concrete with rice husk ash, filtered sand, and superplasticizer were used. Cement and sand was replaced at the levels of 5%, 10%, 15%, 20%, and 25%, 50%, 75%, 100% respectively. From the test results, it was observed that rice husk ash SCC and rice husk ash filtered sand SCC has shown better performance than conventional concrete. Keywords: fresh properties, durability properties, self-compacting concrete, SCC, rice husk ash, RHA, filtered sand, FS, sulfate resistance, sodium sulfate, Na2SO4. Introduction. Concrete is a widely used construction material for various types of structures due to structural stability and strength. All the materials required producing such huge quantities of concrete come from the Earth's crust. Thus, it deflects its resources every year, creating ecological strains. On the other hand, human activities on Earth produce solid wastes in considerable quantities of over 2,500/mt per year, including industrial wastes, agricultural wastes, and wastes from rural and urban societies. Recent technological development has shown that these materials are valuable as inorganic and organic resources and can produce various useful products. Amongst the solid wastes, the most prominent ones are fly ash, blast furnace slag, rice husk ash, silica fume, and demolished construction materials. From the middle of 20th century, there had been an increase in the consumption of mineral admixtures by the cement and concrete industries. This increasing demand for cement and concrete is met by partial cement replacement. Substantial energy and cost savings can result when industrial byproducts are used as a partial replacement for the energy-intense Portland cement. The use of byproducts is an environmental-friendly method of disposal of large quantities of materials that would otherwise pollute land, water, and air. The current cement production rate of the world, which is approximately 1.2 billion tons/year, is expected to grow exponentially to about 2 billion tons/year by 2015. Most of the increase in demand will be met by the use of supplementary cementing materials. Prior to 1970, RHA was usually produced by uncontrolled combustion, and the ash so produced was crystalline and possessed poor pozzolanic properties. In 1973, Mehta published the first of several papers describing the effect of pyroprocessing parameters on the pozzolanic reactivity of RHA. Based on his research, Pitt designed a fluidized bed furnace for controlled burning of rice husks. By burning the rice husks under a controlled temperature and atmosphere, a highly reactive RHA was obtained. The utilization of RHA as a pozzolanic material in cement and concrete provides several advantages, such as improved strength and durability properties, reduced materials cost due to cement savings, and environmental benefits related to the disposal of waste materials. The main components of concrete are cement, sand, and coarse aggregate. The production of cement adds pollution to the environment is a well-known fact to civil engineers. River sand, which is used as fine aggregate, is becoming very scarce. Sand mining is discouraged to save the rivers of our country. Because of these environmental and economic reasons, it requires thinking about the use of industrial wastes as alternative materials in concrete production, which not only reduce the cost of production of concrete but also controls the pollution relatively. Rice plant is one of the plants that absorbs silica from the soil and assimilates it into its structure during the growth. Smith et al., 1986. Rice husk is the outer covering of the grain of rice plant with a high concentration of silica, generally more than 80 to 85%. Surface soils from tank beds, agricultural fields, and village common lands have been excavated and washed to produce a kind of artificial sand in order to meet the enormous demand known as filtered sand. Only source materials with suitable strength, durability, and shape characteristics should be considered. Production generally involves screening and possible washing. Separating into discrete fractions, recombining, and blending may be necessary. Therefore the utilization of rice husk ash, RHA, and filtered sand, FS, in concrete for the replacement of cement and sand, environmentally and economically advantageous. In the present study, Portland cement and sand was replaced by RHA and FS at various percentages to study strength and durability property sulfate attack. Experimental program. Materials used: cement, ordinary Portland cement of 53 grade confirming to IS 12,269 to 1987 was used for the present experimental investigation. The cement was tested as per the Indian standards IS 4031 to 1988. The test results are given in Table 1. Filtered sand, IS 383-1987 was used. The physical properties obtained on conducting sieve analysis and specific gravity tests for filter sand and for different replacement levels of sand by filter sand is presented in Table 3. The amount of silt content in sand to be used in concrete should be less than 5% according to codal provisions, is 383. If the amount of silt content is higher than 5% affects the strength of concrete. Hence the amount of silt content in the present filtered sand is investigated by using hydrometer test and results shown in Table 4. Coarse aggregates, crushed granite jelly of size 12.5 mm down confirming to IS 383-1987 was used as shown in Table 5. Rice husk ash, the rice husk ash obtained from Matter, Mandya district. RHA used for investigation have tested in the civil aid and the chemical characteristics are given in Table 6. Superplasticizer, polycarboxylic ether-based superplasticizer Glenium 6100 has been used in present research work. Mix proportioning for the present investigation, high-strength self-compacting concrete of grade M70 was aimed. To achieve this grade of concrete, Okamura, Japanese, method of mix design was used. Note, C.SCC convention self-compacting concrete with only cement and natural sand without RHA and FS. The mix proportions obtained for C.SCC of M70 grade is 1:1.12:1.17 is been replaced by RHA and FS in place of cement and natural sand by different percentages, which is tabulated in Table 7. Testing of SCC. It is important to mention that none of the test methods for SCC have yet been standardized and included in Indian Standard Code for the present. The following are some of the features of SCC mentioned in Indian Standard Code is 456-2000. 1. Slump flow, minimum 600 mm. 2. Sufficient amount of fines, 12.5 mm, preferably in the range of 400 kg/m3 to 600 kg/m3. This can be achieved by having sand content more than 38% and using mineral admixture to the order of 25% to 50% by mass of cementitious materials. 3. Use of high-range water reducing, HRWR, admixture and viscosity modifying agent, VMA, in appropriate dosages are permitted. European guidelines for testing, covers number of parameters ranging from material selection, mixture design, and testing methods like slump flow test, L-box test and V-funnel test as recommended by FNARC for determining properties of SCC in fresh state. Most of Indian researchers are following these guidelines to determine the rheological properties of SCC mixes. Testing methods of SCC. Different methods have been developed to characterize the rheological properties of SCC. No single method has been found until date, which characterizes all the relevant workability aspects. Each mix has been tested by more than one test method for the different workability parameters. Following are the tests recommended by European guidelines. A slump flow test. The slump flow test is used to assess the horizontal flow of SCC in the absence of obstructions. The test also indicates resistance to segregation. On lifting the slump cone, filled with concrete, the average diameter of spread of the concrete is measured. It indicates the filling ability of the concrete. V-funnel test. The flowability test of the fresh concrete can be tested with the V-funnel test, whereby the flow time is measured. The funnel is filled with about 2 kgs of concrete and the time taken for it to flow through the apparatus is measured. Shorter flow time indicate greater flowability. See L-box test. This is a widely used test, suitable for laboratory and site use. It accesses filling and passing ability of SCC, and serious lack of suitability can be detected visually. The vertical section of the L-box is filled with concrete, and then the gate is lifted to let the concrete flow into the horizontal section. Blocking ratio, it indicates passing ability of concrete or the dosage to which the passage of concrete through the bars is restricted. Tests conducted. Sulfate attack test. This test was carried out on the specimens of total number of 126 cubes of 100 mm size after 28 and 56 days curing period. The specimens were taken from the curing tank and initial weight was taken. 5% of sodium sulfate, Na2SO4, by weight of water was added with water as per earlier investigators, and a set of specimens were immersed continuously for a period of 28 days to determine the sulfate attack of the concrete with and without RHA along with FS. The concentration of the solution was maintained throughout this period by changing the solution periodically. The specimens were taken out from the sulfate solution after 28 days of continuous soaking. The surface of the cubes were cleaned, weighed, and then tested in the compression testing machine under the uniform rate of loading of 140 kg/cm2/min. The changes in strength of concrete cubes were calculated as per IS 516-1959. Results and discussions. The slump flow characteristics, V-funnel, and L-box of the mixtures satisfies the FNARC requirement. Slump flow decreases with increase in RHA content along with FS. The RHA indicates the increase in the viscosity of concrete. The blocking ratio in L-box test were as per requirement of SCC mixes as laid down by FNARC guidelines. The results are presented in Table 8. The fresh concrete properties compared to FNARC specifications. The slump obtained from RHA-FS-SCC is between 768 mm to 653 mm. The V-funnel time obtained from RHA-FS-SCC is between 2.95 SEC to 5.12 seconds. The H2/H1 ratio obtained from RHA-FS-SCC is between 0.945 to 0.862. The fresh concrete properties of RHA-FS-SCC obtained are within the FNARC specifications. Compressive strength. From the table and fig following observations are made. The partial replacement of cement by RHA alone in C.SCC, RHA-FS-SCC, reduces the weight of C.SCC. With increase in percentage of RHA, the reduction in weight also increases. The weight of RHA-FS-SCC with RHA of 5%, 10%, 15%, and 20% and FS of 0%, A0, B0, C0 and D0, is 2.34, 2.11, 2.00, and 1.99 kgs respectively, whereas weight of C.SCC is 2.4 kg. In addition to the replacement of cement by RHA, the natural sand partially replaced by FS in SCC, A1, A2, A3, A4 series, reduces the weight of RHA-FS-SCC specimen further. For a typical case of RHA-FS-SCC with 10% RHA and FS of 25%, 50%, 75%, and 100%, B1, B2, B3, B4 series, the weights are 2.00, 2.10, 1.99, and 1.98 kgs respectively, whereas the weight of RHA-FS-SCC of B0, 10% RHA and 0% FS, is of 2.11 kg. Hence from the above observations the replacement of cement and natural sand by RHA and FS respectively in SCC, RHA-FS-SCC, reduces the weight of SCC in comparison to C.SCC. From table and fig the following observations are made. The SCC with RHA attains significant strength only after 28 days of curing, unlike conventional self-compacting concrete, 0% RHA, 0% FS, which attains its strength at 28 days of curing. The compressive strength of RHAFS-SCC for different replacement level of FS from 0% to 100% with 5%, 10%, 15%, and 20% of RHA varies between 73.18 N/mm2 to 58.36 N/mm2, 67.54 N/mm2 to 50.36 N/mm2, 53.77 N/mm2 to 42.07 N/mm2 and 45.75 N/mm2 to 37.03 N/mm2 respectively. Whereas compressive strength of conventional SCC is 79.69 N/mm2. The compressive strength of RHAFS-SCC of A series SCC, i.e. 5% RHA and FS of 0%, 25%, 50%, 75%, and 100% are 73.18 N/mm2, 68.44 N/mm2, 70.81 N/mm2, 64.88 N/mm2 and 58.36 N/mm2. Similar variations are observed for RHA of 10%, 15%, and 20%, i.e. B, C and D series. The RHAFS-SCC with replacement of 5%, 10%, 15%, and 20% of RHA and replacement of FS of 50%, A2, B2, C2 and D2, the compressive strength compared to 0% FS, A0, B0, C0 and D0, reduces, it reduces by 3.24%, 2.62%, 14.60%, and 0.60% respectively. And when compared to 25% of FS, A3, B3, C3 and D3, the compressive strength increases, it increases by 3.47%, 3.74%, 9.34%, and 3.75% respectively. The replacement of sand by FS in RHAFS-SCC influences in reduction of the compressive strength. However, the replacement level of FS of 50%, A2, B2, C2 and D2, gives higher strength when compared to other replacement levels of FS. Hence, from the above observations, replacement of cement partially by RHA reduces the compressive strength compared to C.SCC. The compressive strength of RHAFS-SCC is reduced further when natural sand is replaced partially by FS. Sulfate resistance. From the table, it is observed that C.SCC and RHAFS-SCC, A0, B0, C0 and D0, specimens when immersed in 5% Na2SO4 solution doesn't lose its compressive strength, instead it shows a marginal gain in weight. The gain/loss in weights of C.SCC and RHAFS-SCC when immersed in 5% Na2SO4 solution are similar in 28 and 56 days curing period. However, the effect of variation in compressive strengths is higher in the specimens with 56 days of curing period. The percentage gain in strength in RHAFS-SCC of A0, B0, C0 and D0 SCC specimens were found to be 2.68%, 5.20%, 1.91%, and 0.44%, at 28 days curing period, and 4.16%, 1.37%, 6.97%, and 4.68% at 56 days curing period respectively. It is also observed that as the natural sand replaced by FS in RHAFS-SCC, A1A4, B1B4, C1C4, D1D4, immersed in 5% Na2SO4, the strength decreases, and the reduction in strength increases with increase in percent of FS. The strength reduces by 0.35%, 5.15%, 0.79%, 9.48%, 5.21%, 12.97%, 4.38%, 2.52% respectively. The reduction in compressive strength increases considerably when the percent of FS is greater than or equal to 50%. The percent reduction in compressive strengths of A3, A4, B3, B4, C3, C4, and D3, D4 are 6.01%, 5.15%, 7.47%, 9.48%, 8.10, 12.97%, and 1.99%, 2.52% respectively. From all the observations, it can be seen that the resistance to sulfate attack of RHA-FS-SCC specimens with partial replacement of cement with RHA and 0% FS, A0, B0, C0, D0, has more resistance than the C.SCC. However, the partial replacement of natural sand by FS reduces the resistance of sulfate attack. Conclusions. Fresh properties. RHA contributes in the reduction of agricultural waste that is the main cause of environmental problems in agricultural countries. On the other hand, it is an approach to improve the quality of concrete without using costly additives such as silica fume, GGBFS etc. Due to the presence of RHA in SCC along with FS, the required strength of SCC is obtained to actual values, after 56 days of curing, unlike normal concrete which attains the strength at 28 days. The presence of RHA reduces the slump. With the increase in quantity of RHA in SCCs, the reduction in slump also increases. The addition of FS along with RHA further reduces the slump. For D4 mix, 20% RHA plus 100% FS, the slump reduced FRROM 768 mm, conventional SCC mix, to 653 mm. The T500 time increases with the increase in percentage of RHA. The presence of FS further increases the T500 time, i.e., 2.95 SEC to 5.12 seconds. The increase of RHA affects the consistency of flow of SCC. The presence of FS along with RHA add to the increase in reduction of consistency of flow. The V-funnel time increases with the increase in percentage of RHA. The presence of FS further increases the V-funnel time. Durability properties. The RHA-FS-SCC of A0, B0, C0, D0, when immersed in sulfate solution gains weight, the percent gain in weight is higher than the C.SCC. With partial replacement of natural sand by FS of 25% to 100% shows marginal loss in weight for all series of specimens, A, B, C, D. The resistance to sulfate attack of RHA-FS-SCC specimens with replacement level of RHA of 5%, 10%, 15%, and 20% and FS of 0%, A0, B0, C0 and D0, has more resistance than the C.SCC. However, the partial replacement of natural sand by FS reduces the resistance of sulfate attack. Hence the RHA-FS-SCC with replacement of cement by RHA is more durable than the RHA-FS-SCC with replacement of natural sand by filter sand.